Assalamu alaikum students, welcome to lecture number 5 and in this lecture we will be discussing our minor losses. In the previous lecture we discussed major losses and derived equation for that, and this is what we are going to do here for today for the minor losses. And as you remember, we used this equation, the energy equation, and here we put the term for the losses in the pipe that occurs in the pipe, the head losses, and then we wrote this equation that the head losses inside the pipe will be equal to the head losses that are the major head losses, and then the plus the minor head losses. And then we said that the major losses are due to the viscous effects inside the pipe, that inside the pipe these losses will be due to the viscosity of the fluid, and the minor losses are due to viscous effects in the pipe components. We will discuss it shortly, that what those components are and how these losses occur. Then we derived an equation for the major losses, and that equation was equal to the Darcy friction factor, the length over diameter ratio, and the kinetic energy. So what we did, we actually then said that we find the value of F, the Darcy friction factor, with the help of Moody's chart. Moody's chart that we use that chart for that, and for that purpose we need to have some values like on the Moody's chart we have the relative roughness. This is the epsilon that is used for absolute roughness over D. This whole term is called the relative roughness. Then here the Reynolds number, and here we have the Darcy friction factor. So if we know these two values, the Reynolds number and our relative roughness, we can actually plot the value of Darcy friction factor. And to just clarify a point, what we use this table actually to find the value of our epsilon. This is our epsilon, the value of absolute roughness, and this value depends upon the material of the pipe, and as you can see that different pipe material have different value of absolute roughness. So whenever we are going to use that Moody's chart, we will have to find this term, the absolute roughness over diameter, that is called the relative roughness, and for that purpose we will also need to have the Reynolds number, and then we will be able to use the Moody's chart and find our value of Darcy friction factor to find the major losses that are occurring inside the pipe. So now let's head to the minor losses and see how they occur. So the components that affect the flow are, let's see the piping system, and let's see the components that will affect the flow. So here the elbow, as you can see the elbow here, it will change the direction of the fluid. So here some losses will occur. Then there is a T. This T will also change the direction of this fluid, so some losses will occur here. Then you see these components, and then there is a valve. This valve's opening and closing position will affect the flow. It actually controls the flow rate. So these components like these in a piping system actually are the cause of the minor losses. So what the components do, they changing the direction of the flow. So the components affect flow by changing the direction of the flow, by obstructing the flow. As you can see in case of valve, it is like obstructing a flow, and then changing the flow speed by varying the cross-sectional area. For this sentence, a better example is the nozzle. If you remember that we change the cross-section to vary the flow speed. Here the flow will accelerate, and if in case of diffuser, the flow will decelerate. So that's what the components are here for, and some typical components in pipe system. So let's have a look at them. Some typical components are bend, elbows, T's. As you can see, these are the bends, the elbows, the T's right here. If you can use some other color. That here you can see these are the bends, the elbows, the T right here, and then the walls as mentioned here, and sudden expansion or contraction. We will see the diagram of that in a while. Then the gradual expansions and contractions, as I mention the nozzle here and the diffuser here. So these are the gradual contraction expansion examples and the entrance into the pipe system from the reservoir. As you can see here, this is the entrance into the pipe system from the reservoir. This is the reservoir and the exit from pipe system into the reservoir. Here in this example right here, this is the entrance into the reservoir from the pipe system. So these are some typical components of a piping system, and let's have a look at this diagram. As you can see right here, that this is the bend right here, this is the elbow. This is what the example of sudden contraction is, that the diameter of the pipe is changing suddenly, and this is the below here is the example of sudden contraction, sudden expansion. This is the sudden expansion, that the diameter of the pipe is again changing abruptly. Not in case of nozzles. As you can see, in case of nozzles, the diameter change over some distance, not abruptly, and in case of diffuser too, the diameter does not abruptly change. So this was the example of sudden contraction, and this is the example of sudden expansion. So as you can see in these diagrams, that you are observing some recirculation regions like this region. What happens here is the flow separates around this corner. Due to this corner, as you can see, these two corners, the flow separates. So when it separates, then the fluid that travels along, it has to fill that space up. So it recirculates. And eddies are created. As you can see right here, that a sharp bend is actually causing these recirculation regions right here. These are the recirculation regions, and these recirculation regions are responsible for making eddies, and these eddies actually results in the minor losses inside the pipe. And that's why we say that these minor losses are due to the different piping components. If the flow direction changes rapidly, as stated here, regions of separated flow are generated. As you can see, these are the regions of separated flow, and what happens is there the eddies form and they enhance the losses. So that's how inside the piping system these components results in minor losses. Inside these components, eddies are generated, and those eddies are actually contributing to the minor losses. So the geometries of most components are too complicated to predict HL mining theoretically. That's what we already discussed when we started fluid mechanics, that most of the equations that you see are not theoretically derived, because there are certain scenarios in which we cannot theoretically derive an equation. For example, we talked about the turbulent flow, that it is not theoretically feasible for us, or we do not have that much facilities to actually derive equations for such flows. So this is also the case for the HL minor, the minor head losses that occur inside the pipes. So what we do, we use this equation. We will use this equation to calculate the minor losses, and here you see the term K. This is the loss coefficient. This K is called the loss coefficient, and is the dimensionless loss coefficient that will be used for minor losses for different components, and it is obtained, as we said, experimentally. So factors that impact K value. What are the factors that are impacting the value of the loss coefficient? So these factors are the size of the component, the geometry of the component, the Reynolds number, the type of connection with the pipe, proximity to other components, and the age of the components, because a lot of pipes are made of different type of metals, so they rust, and also internal layers of water sometimes form due to the different conditions of different fluids. So this is what the factors that impact the K value. So if we see the K value, and this is also called KL, this is the due to loss coefficient. The KL is majorly impacted by the geometry of the components and the Reynolds number. As you can see, the size of the components, the geometry, the type of connection with the pipe, the proximity and age, all are related to the geometry, and there is one component that is related to the flow, that is the Reynolds number. So the loss coefficient is mainly affected by the geometry and the Reynolds number of the flow and geometry of the components. So the loss coefficient values are reported in tables using equations, charts and nomographs, and we will have a look at them in a while. But first, for example, let's say that if a component like nozzle, its diameter is always changing. This is a nozzle and its diameter is changing. So when we have a nozzle, then the designer will have to specify that which section of nozzle we are going to use the average velocity value to calculate the HL minor, because as you can see from the equation of HL minor, that here the average velocity value is used. So due to the changing diameter of a nozzle, the designer will have to specify that which section we should use, or for section 1 or section 2 to take the velocity at section 1 or section 2, or if it is a piping system like this, and if let's say a nozzle is attached right here, so which section we are going to use, this section 2 or this section 1 for using the average velocity value in calculating the minor losses. So in any problem that have to be specified so that we can calculate the minor losses using the average velocity value. Moreover, the minor head losses between the inlet and the outlet in the pipe system is the sum of the minor losses of all the components. So for example, in this system you can see that the fluid is entering here and exiting right there, and we have three components. We have one elbow, a second elbow and a valve. So in this sort of examples, what we will use, we will actually write an equation that HL minor for component 1, HL minor for component 2 and HL minor for that valve, and we will write an equation like this. This is the overall equation, and we will spread it for all these three components, for the elbow 1, the elbow 2 and the valve. As you can see, the elbow 1, elbow 2 and the valve. So we will spread the equation like this. We will add the minor losses for each and every component, but as you can see right here, the diameter of the pipe is not changing. So in this case, when the diameter of the pipe is not changing, then we will take the term V square over 2G common, and we will just add these loss coefficients for elbow 1 plus K for elbow 2 plus K for the valve. So this is how we are going to do that. We are taking this term common because the pipe diameter is not changing. So if the pipe diameter is not changing along the flow, so the velocity will not change, and the only terms that will be added and multiplied with this term is the loss coefficient for each component, the elbow 1 in this case, the elbow 2 and the valve. So this is how we are going to approach problems whenever we are faced with such systems in which the pipe diameter is not changing. So we will just take the velocity component common and multiply it with the sum of the loss coefficient for different components. And this is what we just discussed. We will actually take this term V square over 2G common, and in the bracket inside we will add the loss coefficient for the different components. As you can see, we have three components right here. So this is how we are going to approach minor loss problems and the piping system related to such problems. Then we will discuss some charts. As we said that we use charts and nomographs and tables to see the value of our minor loss coefficient, the loss coefficient KL, as you can see. So in case of smooth entrance, as you can see that the edges of the pipes here are smooth. So in such scenarios where the flow is entering, so along this band right here, how will the value of KL be affected? So the value of KL is affected by the ratio of the radius of this curve over the diameter of this pipe. So the entrance loss coefficient as mentioned right here as a function of rounding of the inlet edge. So the more the edge is round, the more the KL value will be less, as you can see from this curve right here. As we increase the value of this ratio, it means that we are increasing the radius of the curve, so the value of the KL, the loss coefficient, will drop. That means that the losses are actually reducing. Then this is the example of a sudden expansion, and as you can see here, the loss coefficient value is dependent on the ratio of this area, the minor area, to the major area. And as you can see, if this ratio A1 is equal to A2, then there is no loss coefficient, because A1 is equal to A2 means that the pipe has a uniform diameter, its diameter is not changing. But if its diameter is changing abruptly and it causes sudden expansion, then the loss coefficient will have the value, and it means that the minor losses in this sort of component will occur. Then we have a sudden contraction. As you can see that the fluid is flowing and then the diameter suddenly changes. So this is the sudden contraction, and here the ratio is A2 over A1, the smaller diameter over the major diameter, and this is what it will be dependent on. Our loss coefficient will be dependent on this ratio, and this loss coefficient for a sudden contraction, this was for the sudden expansion, and this was for a round curve. So this is how the KL value can be read from such graphs for different type of components. Then we have this component right here, and as you can see, it is a 90-degree bend, and this bend is a smooth bend. So this here the loss coefficient will be dependent on this ratio, the R over D ratio, the radius of this center of this pipe. As you can see from this is the center and this is the radius. So this radius over the diameter of the pipe. So this ratio is responsible for the loss coefficient in such geometries. And then we have an example of a diffuser. As you can see that the flow is here entering, and then the diameter is changing slowly, so it will actually reduce the velocity at this point. So for this scenario, the value of loss coefficient is dependent on the theta, that is this angle right here, this theta right here. So how abruptly this changes, it is dependent on the value of the loss coefficient. So these are the different charts that we use to actually determine the value of KL, as we already mentioned. Then as you can see, we have different tables for different components. As you can see right here, these are the elbows, and different type of elbows have different values of loss coefficients. And then you see 180-degree return bands, you see such components, and they have different value of loss coefficients. And then you see T's, the T's that are used to connect different types. So they have different values of KL. And then you see union threads. These are, and there, this is the union, it is threaded, so it have its own value of KL. And then there are different type of walls, as you can see, a globe fully open, angle fully open if it is closed, and then different types, and there are different values of KL. So as we mentioned that we will use different charts and these tables as they are given as such to write the values of our loss coefficients to calculate the minor losses inside the piping system. Then we have two types of mainly two types, you can say three types of piping system, where there is a single pipe, so it is a single pipe system. If there are multiple pipes, then it is a multi-pipe system. So we will consider two classes of piping system, those containing a single pipe and their length may be interrupted by various components as we saw earlier. And then those containing multiple pipes, and this multiple piping system can be arranged in parallel, in series, or in network configuration. So we will have a look at them, and we will solve different problems. But to do that, we will have to categorize that what different pipe flow problems can be. So pipe flow problems can be categorized by what parameters are given, and what is to be calculated. So there are three types of flow problems, and as you can see from this table, uh, these are tables and these charts are from your Munson book, so you can also go through the book and find them there. And there are pipe flow types is type 1, type 2 and type 3. And as you can see in type 1, what is given, the fluid properties are given, uh, the pipe geometry is given, the flow properties are given. What you will have to find is you will have to determine the pressure or the head losses. This is the type 1 type of pipe flow problems. Then in type 2, the fluid properties are given, the pipe geometry is given, and what you will have to do, you will have to calculate the flow rates and the average velocity, and the pressure drop or the head losses will also be given. In type 3, you will be again given the fluid properties. You will have to find the diameter. You will have to find the diameter of the pipe system, and the length, the reference there will be given, the flow rates will be given, and the pressure drop will be given. So these are the different type of piping systems. Again, they are single pipe, multiple pipe, and then they are further categorized into three types on the basis of what values we are given, what variables we are given. Either we are given the fluid property, the pipe geometry, the flow properties, and the pressure drop, etc. And then they are categorized in three types, type 1, 2, 3, on the basis of what is given and what has to be determined in different piping system problems. Now let's have a look at this example. This example is example 8.8 from your Munson book, and this is type 1. Type 1 is, as you can remember from the previous slide, type 1 was to determine the pressure drop or the head losses. So this is what we are going to do in this example, and what we are given, we have water at 60°F flows from the basement to the second floor through 0.75 inch uh, copper pipe, drawing, it is drawn tubing at a rate of 12 gallons per minute or 0.0267 cubic feet per second, and exits through a faucet uh, of diameter 0.50 inches as shown in figure. Let's look at the figure. This is the piping system, and here the water enters, and here through the faucet it exits. So the parameters that are given is the diameter of the pipe. We all know that this is the copper pipe, so this will come in handy when we find the minor losses. We will have to look at the copper pipe properties. Sorry, for in case of major losses, we will have to find the Darcy friction factor by using this copper pipe material to see the value of the epsilon, that is the roughness of the pipe, absolute roughness of the pipe. So what we will have to determine is to determine the pressure at point 1. This is point 1. This given is point 1. So we will have to determine the pressure at point 1 under different conditions. In condition A, all losses are neglected, so we will not consider any losses under condition A. In condition B, the only losses included are the major losses, and again in condition C, all losses are included. It means we will have to take the major and the minor losses too. So this is how we are going to find the pressure at point 1. This is our at point 1, and now let's look at our some of the things that we can find from the data that is given to us. And since the pipe diameter is not changing, so we can actually use the flow rate and our area that will be that can be calculated from the diameter that is given. So we can actually find our velocity at point 1. So V1 is equal to Q over A1. So we know the value of q, we can find our area by using pi by 4 d square, and we can actually find our v1, and v1's come out to be 8.70 foot per second. This is our v1, and the fluid properties are the density is given in slug per cubic feet, the viscosity is given. You can see table B.1. It is water at 60 degree Fahrenheit, so you will have to read these values of density and viscosity at this temperature. So then we can actually find the Reynolds number. We know the density, the velocity, the diameter, the viscosity. So we can actually find the Reynolds number, and Reynolds number comes out to be 45,000, and we know that if it is greater than 4,000, then it is in the turbulent regime. So here we can say that it is in the turbulent regime, the flow is turbulent, and the governing equation for either case A, B or C is the energy equation that we already discussed previously. And the energy equation, as you can know, is this, and let's fill some space first. This is our energy equation, and in this energy equation will be applied. As you remember, we used to apply Bernoulli equation on 2 points that were mentioned, or that were given in a certain problem, and then we will cancel out certain values to simplify our equation. So this is what we are going to do in pipe flow problems. We will actually apply this energy equation, what we are given two sections, that is section 1 where the pressure is required, and then there is section 2 where the faucet is installed. So we will apply this equation on these 2 points. So here, this is how this equation will look like. That is P1 over gamma plus the kinetic energy correction factor multiplied by the V1 square divided by 2G plus the elevation at point 1, and then at point 2, that is P2 over gamma plus the kinetic energy factor multiplied by V2 square divided by 2G plus Z2, that is the elevation at point 2, and the head losses. So in point A, we will have to neglect all the losses. So this term, the head losses term, will be removed when we solve that solve for pressure by neglecting all the losses. So what else will happen? Point 1 is the reference point for point 2, so the Z1 will also be equal to 0. The elevation at this point, Z1 will be 0. Elevation at point 2 is 20 feet, as you can see, from this point to this point, and then from this point to this point, this 10 and 10 will add up to be 20 feet. And at point 2 actually exits into the atmosphere. So as you already know from your FM1 that whenever the flow is exiting an atmosphere or is in contact with the atmosphere, then at that point we take the pressure is equal to 0. So this is what we are going to do. And then to find the value of gamma, we know that it is equal to density into gravitational acceleration. We can find that, we have the values. And then we'll also find the outlet velocity, because the flow is exiting through a faucet, and the faucet diameter here is changing, and its diameter is 0.50. So we will again use the same value. We will use the same values, and that is for the flow rate, and we will put the area at A2. The A2 will be pi by 4 into diameter d square, this diameter. So we will find area A2 to find the V2, that is Q over A2. So the flow rate will remain the same, that is given in the statement, and we will have to find the area at point 2, and then we will get our velocity at point 2, and that velocity comes out to be 19.6 foot per second. So we assume that the kinetic energy coefficient alpha 1 and alpha 2 are unity, and that assumptions can only be made if we say that our flow profile is uniform. As you remember that we said that for uniform flow profiles, alpha is equal to 1, and as they transform, then the value of alpha changes, and then the value of alpha for parabolic flow is actually 2. So because our flow is turbulent, and as you already know, the turbulent velocity profile is like this. It is of uniform. It is uniform. So that's why we are taking this assumption that our kinetic energy correction factors are equal to the unity, and for that you will need some info from the previous lectures to understand that point. So this is reasonable because turbulent velocity profiles are nearly uniform across the pipe. So now let's put all these assumptions in this equation and solve it. This is how our equation will look like if we arrange it. So we will have pressure at P1 that we are going to find is equal to gamma Z2 plus half rho V2 square minus V1 square plus gamma HL. This left and right hand side is multiplied by gamma, so that's how you will get these equations. Z1 is cancelled out, P2 is cancelled out, so you are left with these terms, and we will arrange this equation for P1 because we are required to find the pressure at point 1. Now this is what our equation will look like for P1, and this is our piping system that we saw earlier. And after solving this, what we will do, we will actually put HL is equal to 0 because this was the condition A that we were given. So after solving this, what we will going to get is pressure P1, and here we are not actually included any losses inside this piping system between point 1 and point 2. So what will this pressure P1 at P1 pressure is 10.7 pound per square inch, and at P2 we already know that it is 0. So how does this pressure drop occurs from point 1 to point 2? For that, what we are going to see, an interesting comment. So the pressure drop, the amount due to elevation change. There is some contribution from the elevation. As you can see that this term, that gamma z in this equation, gamma z, this term represents the elevation. So some of that contribution from the elevation change and the amount due to increase in kinetic energy, the kinetic energy also increases. So this term in the equation, that contributes to the pressure drop also, this kinetic energy term. Because you can see that at V1 our velocity is at 0.70 feet per second, and at point 2 our velocity actually increases. So it increases because the pressure drops. So this pressure drops from point 1 to point 2, and that for that drop some of the elevation changes are responsible, and the kinetic energy also changes as a result of that. Because if you remind the Bernoulli equation, we discussed that the Bernoulli equation is actually the equation of motion for fluid. So how does the fluid motion change when the pressure changes and the elevation changes? So here the pressure changes due to the elevation, and ultimately the velocity also changes, and the pressure drop from point 1 to point 2 occurs. From point 1 it is 10.7 psi, and point 2 it is 0, as we already saw previously. So this pressure drop occurs like this. So now let's move on to point B, and in point B what we are going to do, we are going to add the major losses in this equation, and for major losses we will need the Darcy friction coefficient and our length of the piping system. So let's see how we are going to find that. To calculate the Darcy friction factor, we are going to use our table 1 that we saw earlier. And table 1, let's look at table 1, and in table 8.1, sorry, in table 8.1 there were different type of pipes, and what we have a drawn tubing. We have a drawn tubing, and we will use this table to see the value of our epsilon, that is the absolute roughness, and the value of epsilon for drawn tubing is this in feet, and this is in millimeters. So we will use this value for our value of epsilon, and then we will calculate this ratio, the relative roughness, and we already know our Reynolds number, that is 45,000. So now we can actually use the move this chart to plot our value for the Darcy friction factor and to put it in this equation and find our major losses. We also need the length, the L right here. So the length is the total length of the pipe. So here it is 15 feet, then it is again 5 feet, and then it is 10 feet and 10 feet, and then plus 20. So overall the pipe diameter is, the pipe length is 60 feet. If you add all these lengths, it will come out to be 60 feet, that is 15, 10, 25, then this is 10, 35, and then 5 is 40, and then 10, 10, that is 50 and 60. So this is the length of our piping system. Actually we will add the length of each and every pipe. So this is what this value will be. L will be 60 feet, and the elevation and kinetic energy portion will be the same as equation 1 that we derived for finding the pressure at point 1 without the losses. So we will use the same equation, but now we will just add the term of the major losses, and then we will find our pressure, and it will come out to be 21.3 psi. And as you can now see that the pressure is high, that the pressure drop is actually different. We saw here that P1 without the losses was 10.7 psi. But if we include the losses, then actually the pressure is dropping from a much higher value. It is dropping from 21.3 to 0. So that extra bit beyond 10.7 is due to the major losses inside the pipe. And as mentioned here, of the pressure drop, the amount due to pipe friction is 10.6 psi. Now we will solve this same problem for condition C, and in condition C we will include all the losses, that is the major losses and the minor losses. So this is how our equation will look like, and now in this term we will add both the losses that we have. So this is the same equation. Now you are seeing these two terms. This is for the major loss, as we already calculated, and we will calculate the minor loss. So for that we will have to solve this term and see some values from the table for this K, that is the loss coefficient. So for K, as you can see, this 21.3 is the contribution for the major losses, and the loss coefficients of the components KL. There are different components in this diagram. As you can see, there are 4 elbows, 1, 2, 3, 4. So we will actually see their values, and their values are 1.5. So we will add 1.54 times, and then there is a wide open globe valve. We will see its value, and it's 10. And then there is a faucet right here, and for faucet they say that KL is equal to 2. It is not given in this table, but except for loss coefficient of the faucet, which is given in figure, this KL is equal to 2. So we will take these values and will basically add them in this equation and solve them for the minor losses. So this is what says done here. We are actually solving this for the minor losses. This is the density, this is the velocity term, and then 10 is for the globe valve, and then we have 4 regular 90-degree threaded elbows. For that we have to multiply 4 times 1.5, and then we have this 2. So from that our minor losses comes out to be this much pound per foot square, and then in pound per square inch, that is this is 9.17. So now our pressure P1, if we add this minor loss 2, it will comes out to be 30.5 pound per square inch. So basically this is the more realistic value of pressure at P1, and pressure at P1 is 30.5 and it is dropping to 0.2, that is 0. So now we can say that we have a more realistic value that the pressure is actually dropping from 30.5 to 0 psi's, and these are the major contributing factors are the minor losses and the major losses, and then due to the elevation and kinetic energy changes, the pressure is also dropping as we saw in part A. So this was your type 1 flow problem related to a piping system, a single piping system. Here is the graphical representation of the pressure drop that is occurring in this piping system, and it is given, this is on the vertical axis is the pressure, and on the horizontal axis this is the distance. So we know that the total length of the piping system is 60 feet. So here different points are given, and here the location 1 represents this location, 3 represents this location, 4 represents this location, and so on and so forth. 5, 6, 7, 8, and so on and so forth up to the point 2 where the pressure is 0. So here you can see that how the pressure changes along the length of the pipe, and here two conditions are given, A and C. In A we included no losses, and in C we included all the losses. So this thick line is for no losses, and as you can see the pressure changes due to the elevation and the change in the kinetic energy from 10.7 to 0. And when we include the losses, so the pressure jumps to 30.5 psi. This is a more realistic value, and then it drops from here to this value. So this is the graphic representation of the pressure change or the pressure drop that is occurring in this piping system.